Hello and welcome to Kickstart online webinar here at Glasgow Caledonian University. My name is Branka Dimitrijević and I will moderate today's event. If you are joining us for the first time, I should say that this is a project of 7 Scottish universities and that we disseminate outcomes of feasibility studies and academic consultancies undertaken by these universities for medium and small sized companies operating in Scotland. The focus of these studies is on sustainable building design and refurbishment. The project is funded by European Regional Development Fund and Scottish Government CIC program, which is now managed by Scottish Funding Council. This is a live event, so if there is a fire alarm, we will have to stop, but we will continue later. If you cannot join us, you can always watch video recording of this webinar, which will be published in due course on our website. We plan to complete presentations around 1:30, but you can start asking questions by using chat facility at any point during the webinar, and the answers will be provided after presentations. And we plan to close around 2 o'clock. We also offer a live transcription service as a part of our online broadcasts. The presentation is transcribed live in a pop-up window as the webinar takes place. By providing this service, we hope to make our webinars as accessible as possible. The instructions are provided in a login email that you have received this morning. So today's seminar title is Thermal and Humidity Testing of a Hard-to-Treat Wall. And the speakers are Julio Bros Williamson of Edinburgh Napier University and Wilson Shaw of BCA Insulation. I would kindly now ask Julio to start with his presentation.
Thank you very much and good afternoon everyone. Thank you for joining us. I would like to start as always thanking Branka and her team at Kickstart for all the work and also this kind of communication that we've had with the BCA company at this stage. I would like to really start with an introduction to the work that we've developed around thermal and condensation analysis of typical solid walls in Scotland, which we feel is quite important to bring into further research and also to bring in the practical aspects which BCA Insulation are ready to bring forward, and also our academic input in terms of analysis and further work around the performance of thermal aspects in solid walls. Just to start off the presentation, I would like just to kind of talk through the areas that we'll be talking and presenting today. A brief introduction, followed by some aims and objectives in terms of what this feasibility study brings to the table and also provides, and very importantly the methodology of our testing, which really talks about the areas that we've addressed and also where we've taken that methodology from other references, etc. Also more in focus of the actual the testing that we did, talking about the location and in this case a case study that we'll be dealing with, and then the results that we've obtained throughout the study, followed by some conclusions and further work that we develop. So as an introduction, ourselves from Edinburgh Napier University, the Scottish Energy Centre, we provide consultancy on building and energy matters, renewables as well. We were approached by BCA Insulation to develop this analysis of a solid wall that has gone through a refurbishment stage. They had lots of concerns in terms of the performance of it, both thermally and also in terms of interstitial condensation build-up within the different layers. So they were keen for us as an academic partner to engage into this analysis and this research. it was really focusing on the improvement of buildings. There is a big focus on retrofit these days, but more importantly, I think, is the proper way in which we retrofit our buildings, especially the ones in Scotland that have some particular building forms and various different aspects to them that can differ from other regions of Britain. So it's important that we address the Scottish aspect of it. The concern in this case study was really to address the thermal aspects, the thermal comfort of the building, and also to reduce heating bills, which has been a wide focus in terms of improving properties of this type. The following slide is really just setting the scene on what type of buildings we've been addressing, and as part of this case study, we're looking at sandstone type solid walls, which are quite common in central Scotland and throughout Scotland. In this particular scenario, it's a red sandstone type wall, solid wall. And it's been a focus of a great deal of analysis and further research that both BCA Insulation and ourselves have been developing with Historic Scotland, who are obviously quite concerned about historic buildings, the heritage side of things, and the conservation of them. So it's important for us. But it's not just been buildings that have got a heavy historical background to them. It's also buildings that are within the mesh of our cities and towns, and they could be your very simple forms of tenements, and also closer to this day and age, maybe six flat blocketed apartments where there could be other issues. So there's different solutions, different elements of retrofit that are aimed at different types of buildings, and Historic Scotland are quite interested in that as well. So BCA Insulation, ourselves, and Historic Scotland have been working together quite strongly. I will now pass over to Wilson Shaw from BCA Insulation, who will give us a bit of a background of their company and what they do. Thank you. Wilson.
Thank you, Julio. BCA Insulation have been running now for nearly 15 years, and we, from our initial conception, had the aim to become a specialist insulation company and not settle strictly for the basic loft and cavity wall measures of the past. Partly this was through desire and the fact that a lot of the staff came from a professional construction background, but also it was partly through necessity, as we had to find our own path in the market. As the company has grown over the years, we've had a very open arm approach to new technologies, which has served us well, and we are now currently involved in installing loft and cavity systems, many of each, as well as internal and external wall systems through various projects, including the Energy Assistance Package, CERT and CESP before the end of it, UHIS, and hopefully on into Eco and Green Deal. In the delivering of these measures, in particular for UHIS, we have now installed well over 150 internal wall insulation installations, and have, as our experience has gone along, gathered lots of interesting insights into the obstacles and challenges one faces with internal wall. But given that there is just over 465,000 pre-1919 properties in Scotland alone, internal wall insulation is certainly an area that needs to be looked at, and these obstacles need to be overcome. We've also been lucky enough to be involved in several Historic Scotland case studies, and that's been a great learning process for us, and also, if anything, or if nothing else, has also maybe created a bit of a desire to test conventional theory, as this is what Historic Scotland have done with great success over the period. The problem we see with internal solid wall insulation is that there are many ways it could be done. There are many theories of what is required with regards to the protection of the fabric and the use of hygrothermic materials, etc. But there is a challenge. It has to be brought in on budget, and with ECO there will be budgets to work with, and with Green Deal plans there will be golden rules to work to. And it has to be done in a way that's acceptable to the client. And this is where we were struggling, because there are certain aspects of conventional theory and good practice guides that would require details that were not acceptable to clients or would be at a cost that was unacceptable to ECO and Green Deal. And this is why we wanted to embark on this research to see if the difference in the Scottish details when compared to English details meant that a lot of these obstacles could be overcome by simply tweaking the method of instruction. So I'll hand you back now to Julio.
Thanks, Wilson. I mean, you've highlighted definitely the importance of it, and this case study looks at an internal wall insulation example, and we'll look on some of the test results. But first of all, just really talking about what the aims and objectives were of this study. Really, we're trying to look at the hygrothermal behaviour of the building, and particularly this wall. In this case, and I'll talk about it further, it's one room in particular that's been retrofitted with this internal lining and an internal insulation. So it's important to see how that wall is behaving after this insulation has been applied, so that there's no detrimental problems to the building fabric, whether it's or the thermal comfort of the room, whether it's on the building structure of the integral part of the wall, or it can produce a series of health issues in terms of mould or condensation build-up, etc., etc. So that was the kind of aim of it, to look at whether this insulation, this upgrade, will be suitable for this type of wall, and to really measure this, and together with the detailing, try and also have that in line. So there's been similar studies with other projects that we've been involved with. The objective really is to see if this solid wall was able to withstand long-term situations, if it was possible to still be in line with the original building fabric. So that was important, and also really looking at ways in which we could still work with interior decoration, and also work with interior problems that different walls may have. In this instance, there is a very interesting cornice in the top of the wall, and BCA have experienced very similar examples in other case studies and other projects that they've been involved in that the client is really interested in maintaining and keeping as much as possible the kind of architectural decoration around it. So in this case, they're insulating right below the cornice, meaning around 95% wall covering of internal insulation, and leaving an uninsulated part at the top, just below the cornice, including the cornice as well. So that was part of the testing and the methodology around this analysis. In terms of what we did, what type of study and what monitoring we conducted, there was three main elements, three testing regimes. We did an infrared thermography study of the different walls, both the insulated wall and also the adjacent walls, and see what impact that brought. We also did an in situ U value testing of the actual wall, the insulated wall, and the uninsulated wall just below the cornice. And we also conducted interstitial condensation in situ testing by inserting hygroclip devices into the wall at the cavity level. So that was important for us to kind of have those three elements of the testing that would really point out whether there was any issues appearing within the actual use of the room, and how that influenced the performance of the wall. I mean, here we can see in these photographs just a kind of snapshot of one of the issues around an adjacent part of that wall, which is a dormer kind of window, which is leaking quite a lot of energy. So it was good to have that comparison between different surfaces of the wall. And this is just a couple of a photograph of our equipment with a logging device, the in situ heat flux discs, and also our interstitial hygroclips that are inserted into the wall. And finally these, which we call tiny tags, that are loggers as well of temperature and humidity. So these were good equipment, really, the equipment that we have available for conducting this work. The testing was performed in different stages. The window of testing, really, the period of testing was throughout the month of October in 2012. We recognise that this is just a month-long testing, and we've been doing continuous testing, as I'll explain later on. So really, the results in this webinar look at a glimpse of the start, kind of the first period of the heating season back last year. But we conducted the infrared thermography in a cold kind of night without the influence of solar radiation. Tried to obviously have a temperature difference between the inside and the outside, and to really highlight areas of heat leakage. In terms of the in situ U values, they were kept for 20 days throughout the month of October, which is enough for them to stabilise and to give us some good information for later on calculate it with other kind of procedures. And finally, the in situ interstitial condensation, which, as I've mentioned, was throughout the month of October, but is continuous as we speak. Just briefly on the methodology of each one of them, and how we've taken benchmarking, and also how we referred to other documents and other references that obviously feed into the way that we're performing our work. We've relied and we've been reading a lot of information on similar work, especially from Dr. Baker from Glasgow Caledonian University, and also Dr. Caroline Rye, who both of them have been working with Historic Scotland in other case studies, especially on the in situ of U values. And a lot of their calculations and their methodology have been taken on board. We've also, in terms of the calculation of the in situ data that we log and that we obtain from the field study, we refer to the ISO 9698, and that one, that ISO really sets out the different standards and the calculation procedure to obtain an in situ U value. So we've taken that on board quite strongly. In terms of the type of equipment, I've explained roughly, but just a bit more detail on it. We use these heat flux, Huxiflux discs that are that really record a voltage difference between the internal surface and really records this heat flow through that element in that point. And in that period of time. And that information is later on, as I've mentioned, calculated with the use of internal and external temperatures and also surface temperatures of the different elements. So we've positioned these discs, these heat fluxes, both on the insulated wall and also where just below the cornice where there's no insulation, just to get these two elements and to have a comparison of in situ U values. In terms of using the tiny tag loggers, which log both temperature and humidity, they were useful for validating these internal temperatures that were obtained through the use of thermocouples, and also the humidity aspect would be used as well for our interstitial condensation calculations. So it was also useful to leave those on site. So these are a couple of pictures of our equipment. Again, you've got the heat flux discs that are positioned right onto the wall, together with a thermocouple logging surface temperatures. This is our logger here that obviously takes the information from the discs and the thermocouples and logs it for a certain period of time. And our tiny tags, these loggers of temperature and humidity. This photograph here is the wall in question. This is a photograph of an internal element. This is once the insulation has been installed, and we can see the different heat fluxes already positioned at the different heights and different positions of the wall. And this photograph here shows us the external side of the wall, and I'll talk about that later on. In terms of thermography, just quickly, it's important to really highlight what methodology we took. There had to be this temperature difference between the inside and the outside, so a cold night, kind of without any solar radiation influence. The internal infrared thermography images usually show, well, wherever there is heat flux, and wherever there is heat escaping, or there's a thermal bridge, usually that's represented by purple or blue kind of patches around different elements and different areas. So those are the areas in terms of internal shots, internal images, infrared thermography, where we would see a temperature difference in terms of the surfaces. And we'll see in some of the photographs, the images, where we've got very even temperatures of heated surfaces compared to elements where heat loss is appearing. So that's when there's a temperature difference between different parts of the wall. So infrared thermography is a good tool. It's got to be analysed and taken quite seriously, and some elements, some images can be deceiving in terms of making sure that what we are looking at is really heat loss and not something else. Or it could be that it's humidity appearing. It could be that there's air infiltration in that area. So it's difficult to really get as accurate as possible. But with good analysis and a lot of detail, you can get some good elements. In terms of the interstitial condensation analysis, as I've mentioned, we've got probes, hygroclips that have been inserted into the wall. Both of them penetrate the wall at the two locations that I mentioned before. We've got just below the cornice, and also we've got where the wall is, the insulated wall, and they both go into the cavity behind the lath and plaster of this wall. What we're really looking at is this relationship between temperature, humidity internally and externally, and also any vapor pressure difference within internal and external surfaces. In most cases, internal rooms hold moist, hot air, and which later on and transfers itself as moist kind of vapor, and that passes through most of the layers of our walls and can create different humidity patches whenever it reaches a colder surface. So that's really what we're trying to identify, to see whether the wall itself is resisting to this moisture passing through, and if it is, knowing what the actual wall is doing with this moisture buildup, if any. So that's an important aspect of it in terms of our kind of methodology and our results. This slide here really looks at as an example of what we obtain. The theory behind this graph, really, the drawing is really a representation of a wall, which, in line with the graph which is embedded in front of it, can give us an indication of where condensation can build up, interstitial condensation can build up. So we've got our saturated vapor pressure, which is this blue line, which really is calculated through the vapor resistivity of each material and the thermal aspects of the material. So that is the boundary line, really, of how that wall will resist the passage of vapor and vapor pressure, and how it will manage vapor pressure. Obviously, though, whenever circumstances, both internally and externally, in terms of temperature and humidity change, that threshold of saturated vapor can change, and that's where we get this interface vapor pressure, which is taking internal and external conditions, and it's actually charting it against what the wall should be experiencing. So whenever that interface vapor line is above this threshold of saturated vapor, that's where we can experience condensation and interstitial condensation. So, I mean, this slide is just really an example of what could happen. In terms of our boundaries and our temperatures, we've got to take temperatures that are both internal and external, together with the humidity, the relative humidity, and also, if in a later stage I'll explain, interstitial temperature and humidity, which can later be translated into vapor pressure. So those will populate this type of graph. So a bit more about the building in question. It's an end terrace two-storey house. It's located in the town of Wishaw in North Lanarkshire, and it's a wall it's a gable wall that's been going past quite a lot of it's quite an exposed wall in terms of where it's located. So it does suffer from driving rain. It does suffer from some sort of decay at the moment, and that could be a detrimental kind of effect to how it's functioning and internal conditions. We can see a couple of patches here where the sandstone is starting to decay slightly. The case study and the room that we've monitored is in the first floor. and our probes are located roughly in this area here, in the centre of the wall, very close to the chimney stack. So, I mean, previously the wall had experienced some sort of humidity building up, and it was experienced as a survey later on kind of it showed that, and moisture kind of patches showed that due to the chimney that was located very close to that wall, to that gable wall. That was later on fixed and was actually dealt with, and that was actually fixed before our monitoring. So really we were in a position where that wall had dried out, and the issues of any kind of moisture that had built up through the chimney had disappeared. If we had located later on in our results an increase in moisture, that could have been one of our theories. But in this case, it's dried out and it's been dealt with. So these are a couple of images of the room. This is a dormer window that's right next to the wall, and this is the wall itself where there is a kind of area where a previous cupboard was located. But really, this is the original part of the wall, and these are some images. The image shows where there was a patching of what occurred beforehand in terms of the chimney stack and humidity stacking up. So we later on had the retrofit had been, the internal insulation had been located, had been installed. This image shows how the insulation reached the top of the wall, leaving this gap just underneath the cornice, respecting the cornice, and leaving this area uninsulated. As I've mentioned before, we located heat flow mats at the point where the insulation was located and installed, and also just below the cornice. And we did the same thing for the hydro clips. We located them at those points right into the cavity behind the lath and plaster. So, I mean, we've used two hydro clips, and they've been at different thicknesses. Obviously, the insulation presents an increase in thickness of wall, and our probes are able to go right into the insulation and behind the lath and plaster. The first probe, where the insulation was located, it was 80 millimeters into the wall, into the cavity, and the second one was 45 millimeters right into the cavity, so there was less material to go through. As I mentioned, the information and the results that we are presenting today are for the first 4 weeks during the month of October. This is a sketch of that photograph beforehand, but just the location of a lot of our equipment, with the two heat flow mats and also the hydro clips that I mentioned. Also our surface temperature logging equipment and our thermocouples, and our additional internal temperature and humidity loggers. So it was really trying to monitor and to log as much as possible the two scenarios, the insulated and the non-insulated, just below the cornice. In terms of what was used, I mean, this is a cross section of the wall. We can see the first hydro clip going right through just below the cornice into the cavity, and the second one here right through the insulation into the cavity, just before the sandstone wall. And we can see the different materials and the different layers that were used, the original ones and the new ones. The insulation used was a phenolic solid board. together with a kind of plasterboard to obviously receive the interior finish. These red discs are our heat flow mats at 2 different positions. So really that was a good way of representing where these this equipment was located. So that really explains a lot of our methodology and the way we conducted our work. I'll briefly go on to some of the results. In terms of the infrared thermography, I've located and I'll display a couple of the images. We've got both the photograph and the infrared image side by side. As I explained before, the colder patches, the areas that have no insulation or there is temperature differences, are these kind of purple or black kind of patches. And we can see that the insulated wall has actually got even temperatures, which we would expect from insulation. And compared with just below the cornice, where we can see patches of colder surface temperatures, together with the ceiling, where there are also variances in temperatures, but colder than the insulated wall. That's the wall in question. That's the wall that we monitored. But equally, we wanted to look at the rest of the walls adjacent to this one. And I've shown this one before in another slide. This is a dormer window with the dormer sides, the roof part of the dormer, and we can see that there is quite a lot of heat escaping in that patch compared to the insulated wall, which is quite close to it. So it was important to really show the different scenarios on different walls. This is a corner, which is quite interesting, between the dormer element and our insulated wall and the cornice at this level here. So we can see that the dormer and the structure around it is actually conducting quite a lot of heat around it. But equally, we can see the insulation is shielding a lot of that heat at the wall area, and is actually acting as this barrier for heat to escape. So it's a good image to contrast the two. In terms of the in situ U values, as I said before, we used a lot of the methodology and the ISO standards that have been set. We've also, in order to make a proper comparison, we've tried to reproduce these U values and recalculate these values using static U value calculators, and we used the BRE approved U value calculator to give us an idea really of comparison between what is the actual U value together with an expected performance, and we used that the BRE calculator that uses the BR443 standard to do this. We also looked at and read in a bit more detail what's described in documents by Historic Scotland written by Dr. Baker on similar tests. It was quite interesting to see the way in which he modelled the different sandstone walls, and as close as possible with the sandstone and a cavity and a lath and plaster finish. So that was important. And one element that we wanted to highlight was the way that he modelled the sandstone wall. It's not just a solid sandstone. We know that there is mortar involved in obviously the construction of these sandstone walls, but sometimes more than expected. In many cases, Dr. Baker indicates that we have a 60% of sandstone itself and a 40% of of mortar. Now this is due to the fact that a lot of these walls are built as rubble walls, where you might have patches of a lot of mortar blended in and together with rubble sandstone elements. So it's not just your typical ashlar type wall that is very nicely cut, and the pieces are very exact in terms of sizes, etc., and joints, and where you could have less mortar in it. In this case, in a lot of these type of walls, especially in this case study, you're talking about a 60-40 difference, and we've modelled that to be as close as possible. So this is a diagram from Dr. Baker's paper with Historic Scotland, technical paper 10, I think, and that kind of explains this rubble wall, typical rubble wall, where you've got this 60-40% of materials. And these are our results for the in situ U value testing compared to the BRE calculated. We've got below the cornice an expected higher U value compared to the insulated wall. But what's interesting to see is a difference between the actual and the calculated. And Dr. Baker also highlights this in his papers and examples, where you've got the calculated value is in many cases up to 10-15% less than the in situ one. In this case, it can be slightly larger depending on different circumstances of the wall. So in terms of below the cornice, the U value, the calculated one, 1.04, and the actual is 1.27. The same goes for the insulated one, slightly closer to each other, 0.41 in the BRE calculator, and the in situ 0.48. So a slight difference between them, but again we can see a difference between the uninsulated patch just below the cornice and the insulated element, which is a good saving in terms of thermal transmitters. And then, we move on to the interstitial condensation results, which are the elements of the study that are more interesting for PCA insulation. We know that interstitial condensation can be quite harmful, not just for the structure itself of the building and at one moment in time, but also as time goes by, condensation build up and moisture build up in different structures. Timber, for example, can really bring problems to the structure and create structural elements fault. It can also be an aesthetic element in terms of creating mould and different pores around surfaces that can be quite harmful also to people's health, creating asthma and different respiratory problems. So we've got both issues with the structural and the actual development of the building, and also health reasons for the building. In this case, it's a room that's occupied by children. It's one of the bedrooms of one of the occupier's children. So really, it's important to address these issues if they do appear. So in this case, the problems do arise when, and I've explained this slightly, where you've got the vapor diffusion of moisture through the walls, and where it accumulates, and wherever it touches and reaches colder surfaces, that's where you can get this accumulation of moisture that can later create problems. Obviously, you've got different layers within a wall, and each layer will work differently depending on its vapor resistivity. So it's very much a specification task as well in terms of retrofit and what type of insulation material is used and what conditions. In this case, it was an internal insulation. Therefore, we're leaving the gap the void behind the lath and plaster, which we've assumed as being slightly ventilated, to work as it has been all these years. So the effect of having insulation installed would be the next, would be part of the results, and see how that affects the performance of the wall. We divided the results and the testing in two stages. The first stage was looking at a more static and calculated way of looking at the wall. We used a glazer method, which is a very standard procedure in terms of calculating and seeing how interstitial condensation may appear. And then the second phase, or the second stage, would use the in situ data that we've obtained from the Hygro clips, from the analysis throughout the month of October, and use it to calculate and to obtain vapor pressure inside that cavity at the two elements, the two levels. So really, we've got a more static element, just like we did in the U-value comparison. We've got a kind of static and calculated method, and then we've got the use of a field test and in situ data. So we've used those two kind of stages to really compare and to come up with some conclusions. The glazer method is followed by the ISO 13788, and we've used a software to model and apply the glazer method. We use a software called SciMap, developed by CADline, and together with building up different layers of the wall, we can obtain the U-value and also possible locations and areas where interstitial condensation may appear, depending on the performance of each layer of the wall. So we used the glazer method there. But what we did additionally is that we used internal and external temperature and humidity data and implemented it into the software to obtain a glazer model of it. That really helped us to really make this analysis a bit more realistic, not just a kind of predicted temperature and humidity that could be experienced, but more of a realistic one that happened during the month of October. So that was important for us. And what we did in stage 2 was use again the data from internal and external temperatures, but adding a third point, which would be this cavity point, which we would have both, again, temperature and humidity. So instead of having two points, we had a third one, which would be in this cavity, thanks to the Hygro clips. The way we selected, it was impossible to monitor and to show the results for every day of the month of October. So what we did was identify different critical scenarios within the whole monitoring period, and located repeated scenarios where we could experience low temperatures externally and high temperatures with high humidity figures internally. And we noticed that that kind of scenario happened in a number of times throughout the month of October. So we selected one moment in time, one date, one time in October to model this, both in the glazer stage 1 and stage 2. These are some of the tables and the different layers that we modelled, as close as possible to the realistic aspect of the wall. We've got a plasterboard internal finish. This is the insulated wall. We've got this phenolic board insulation, followed by the lath and plaster. We've also got this cavity of 50 millimeters, which is slightly ventilated, we've predicted. And also we've got the sandstone, which I've mentioned is 60-40 together with the mortar and the lime plaster. So we tried to obtain information from these materials as close as possible, together with the vapor resistivity of each one of them, and use them to model it. We did the same thing for the element that wasn't insulated, so just below the cornice, and we obtained information on that as well. So all that information was modelled using the SciMap software. Now this is a stage 1 set of results using the Glaser method. In this case, we've selected this critical point, which was on the 27th of October, and on this time at 6:30 in the morning, we had an external temperature of 0.15, so close to freezing point, and quite a high humidity of 86%. Internally, we had 14%, or just nearly 15 degrees, and a relative humidity of 65%. So that was the kind of moment in time that we modelled, which would be used for stage 1 and stage 2. So in this case, we've got the different layers that the SciMap software models. Again, in the example I explained before, we've got the saturated line, and we've also got the interface line, this red one here. Calculation that doesn't take into account anything that's happening in any point internally. It's only taking data from the internal and external aspects, temperature and humidity. So in this case, it is showing interstitial condensation. This is the insulated wall. If we follow on, oops. We're having a couple of problems with the next slide.
We don't see the slide. Let's see.
Well, just to kind of talk about the next slide, would be the Glaser calculation, where there isn't any insulation, and where we're right below the cornice, and where we've got again a probe right into the cavity. But in this case, just using the Glaser calculation, we've got, and we'll see when the slides come over, that there isn't any interstitial condensation in this point, and that there's no problem in terms of handling moisture at that point. I'm not sure if the slides will come back, but I'll continue with. The next couple of slides will show the in situ data. So this is the second phase, the second stage of the monitoring. We've modelled the way Glaser would show it, the way that methodology would show it, but bearing in mind that only takes into account the two internal and external elements or conditions really of the wall, and doesn't really give us what's happening in between the layers. So that's important, and our probes would give us this extra point that would really tell us a bit more of what's happening behind the lath and plaster and in that cavity. So the way we've represented this, well, this is coming back to what I was talking about, Glaser method, our software package, how it's modelled it, and as I mentioned before, there's no interstitial condensation at any point in the layer. We can see that the interface line is below this saturated kind of vapor line, so there's no interstitial condensation. I've not explained this line here. It's purely just shows a temperature gradient between internally and externally, which has to do with the calculations. But in this case, we're interested in these two lines. So, in terms of the same scenario, the same time in the same period of monitoring, the same critical point as before, but at a different element and a different height of the wall. So no interstitial condensation with the Glaser method. And this is the next slide with our monitored results. I've located here both the Glaser results together with our interstitial field study monitored results. So as we can recall from the previous slide, where we've got insulation, the Glaser method had located interstitial condensation just after the insulation, where the lath and plaster is, the cavity, and right inside the wall. But in fact, when we add this third point using our field tests and our probes, we can see that this third kind of point in the cavity is showing that there isn't any interstitial condensation. This square, this red square, is our measured actual vapor pressure, and the circle, the blue circle, is our kind of saturated vapor pressure, the measured one. So we can see that the measured one is below the saturated, meaning that there isn't any risk of interstitial condensation. And again, we've got this temperature point as well, quite high up. So, as opposed to the Glaser method, and we must remember that we're using the same time, same point in the same time, the same critical time, 27th of October, the same conditions internally and externally, but we're adding this, the data that we've obtained from our probes to give us this third point, and this kind of indication that at this point in time in these critical elements there's no interstitial condensation. And the same goes for the below the cornice. Again, the same conditions. We've got the Glaser method here, which we knew that it wasn't showing interstitial condensation beforehand, and this verifies it once again that the measured actual vapor pressure is below this saturated vapor point. No condensation is appearing, and in this case there's no fear of any moisture buildup. So after, all those three elements of monitoring, of analysis, and really charting up our results, we've come up with some conclusions, and Wilson will also add to these conclusions. But we can clearly see that the Glaser method has predicted that where there is insulation, there's fear of condensation, but we have verified that through adding this third point and obtaining information in that cavity that there isn't any condensation buildup. So that's good in terms of verifying the real conditions of the wall. In terms of the different conditions in above, in terms of the cornice, we've verified once again that there's no interstitial condensation, which Glaser had shown that anyway, but it's good to have that reassurance. What we've concluded really is that there could be some condensation being driven, or most of that condensation is driven up that cavity. We've predicted that it's a slightly ventilated cavity. Therefore, we're seeing, and this is what we're seeing through our analysis, is that the reason that there's no interstitial condensation in both elements is that that moisture is being driven up that cavity and being taken upwards. Now, we think that some of that condensation might be dissipating back into the room at the cornice level, just where the cornice is. That would happen not during the day, especially when the temperatures are quite high internally. It would probably happen when temperatures go down, for example, at night, and there's that temperature difference. We see that possibility of being small, but it could happen. But we are seeing that that condensation is going upwards, and is in this case going up into the attic space and into the roof. That's the way we're kind of interpreting a lot of these results. In terms of looking at the monitored humidity and temperature and humidity patterns inside that cavity, I think it's important to also highlight that throughout the month of October, we saw that in this case the blue line shows the cornice temperature and humidity. Sorry, in this case it's the humidity, and at the insulation wall, insulated wall, is this green line. We can see that humidity is actually stabilizing at this point, but in this case we're seeing that it's actually going up slightly, up to 90%. Now this is during the month of October, where it's quite a short time span. If we look at more data that we've downloaded so far, luckily Wilson and BCA Insulation have asked us to continue the monitoring. We've continued the monitoring throughout the heating season. Our probes are monitoring as we speak and should be taken down by the end of March, where roughly that's when the heating season finishes. But this is a glimpse of what was downloaded quite recently, about a month ago. We can see that both humidities at both points, at below the cornice and where the insulation is, we can see they're actually stabilizing and they're not increasing, which used to be quite a concern. So in this case, they're actually stabilizing and being quite well controlled. If we had experienced humidity rising even more, close to 100%, between 90 and 100%, we would probably start to experience more interstitial condensation. But this isn't the case, and we're seeing that most of it is kind of controlling itself. In terms of BCA's conclusions, I'll pass over to Wilson, where he could probably talk a bit more about what the next stage is.
Okay. Thanks, Julio. I think on behalf of BCA, we can say it is very encouraging results, and we'll see us continue down the line of researching the difference, the different dynamics of Scottish solid wall plaster and lath solutions and constructions in comparison to the English hard plastered solid brick walls, which unfortunately the majority of the systems are designed for at present. As a rule, all roofs, spaces and lofts would be checked to make sure that they're adequately ventilated for a condensation point of view anyway, whether that be for loft insulation. But it is a good point for us to take on board that we should also inspect the lofts for adequate ventilation when the only system we're thinking about is internal wall insulation. I think the exercise with Napier Uni matches the other research that we've been carrying out over the winter in terms of it's thankfully showing that the condensation risk isn't one to overly worry about, and this will motivate us to continue to keep testing things for the rest of this winter at least, and look to provide a bespoke system for stone, plaster and lath buildings that's affordable and includes details that are acceptable to the occupiers. So yeah, I think it's been a successful project in our opinion anyway, and we can look forward to seeing the final results from the next 4 months that were tested.
I think that's important what you highlight, Wilson, in terms of inspecting the roofs. In this case, obviously, that's our theory that this humidity is rising up. But if the roof doesn't have proper ventilation, that humidity rising up would eventually reach a colder spot and condensate, and obviously create some problems there with the timber elements. So that would be the fear. In this case, a lot of the work that BCA does really covers and inspects the roof, makes sure there's proper ventilation, and also that the temperatures in the lofts and those areas that are properly insulated. So that's important.
I think another thing that'd be good to add is that in the early days of doing internal wall insulation, which were maybe 3 years ago, we were doing such small numbers, it was maybe one a month, that there wasn't much could be gained really. We did that on purpose because obviously we didn't want to run before we could walk. But interestingly, as we went back and spoken to customers installed 3 years ago, with a view to finding out if they've witnessed any issues with condensation or the like, the first thing that they say is, wow, what a difference. Significant savings, life-changing savings, quality of life differences. Even though we're leaving a gap in this solution, it is still making a big difference to the heat retention in the house. None of the projects that have been installed going back to 2009, even in the earliest, have reported any incidents of condensation mould. And one of the other research projects we're doing just now is going back and fitting monitors in those early projects and taking readings on the humidity levels in the cavity and the surface temperatures. So no, it's all very exciting. But I thought it was worth making that point, that the people in the houses are noticing a tremendous difference in their comfort levels and their heating bills, and thankfully not experiencing any problems. And this research and other research kind of fits in with that perfectly, which has included high-level modelling and the fitting of monitors in other projects that have been installed some years ago.
Thanks very much.
Thank you very much, Julio and Wilson. While we are waiting for questions from our online viewers, I just want to apologize if you have noticed any interruptions during the transmission. We had a little problems here, but maybe you have not. But I hope that you could follow Julio's presentation. There was a lot of technical information there, a lot to understand and digest. And let's see, we have some questions and we can see them now. Here is the first one from Dave Tremlin of Conservation Joinery Services. Julio, you spoke at the start of a distinction between Scottish and English construction. For the benefit of we English viewers, can you explain what difference that distinction implies?
It was mainly on the majority of types of walls that could be probably majority brick type walls, the use of lath and plaster, different types of walls. I mean, Scotland tends to use more sandstone, limestone, etc. type of walls, and down south and in England it's could be more aimed at single walled brick walls in whatever shape and form. So that's really, I think you talked about that, Wilson, earlier.
Yeah, I think it was quite a surprise to us to find out that from the 1780s to the 1920s in Scotland the typical form of construction was to use local stone with a plaster and lath finish to take out the irregular surface of the stone on the inside face whilst the outside was dressed. And also was surprised to learn that the use of bricks was far more common in England than Scotland, going back 200 years or so. So that's the main differences. And unfortunately, most good practice guides and manufacturers' recommendations for internal solid wall feature hard plastered solid brick details rather than the plaster and lath cavity stone details.
A question from Sophie Pursmakers at University College London. Rye-Baker methodology is not the same as ISO 9869. So which one did you use for sensor placement error analysis and data analysis?
We used mainly Baker and Rye for their examples, but in terms of the calculation and the methodology of taking on board the different formulas for internal and surface temperatures, we used ISO 9869.
A question from Kevin Toner of IHBC. 80% internal relative humidity and 70% external relative humidity seems odd. Oh, but just see in your scenario 4 and onward, which appears closer to reality, 64.5 and 86. I trust the methodology graph was simply a gradient calculator test using hypothetical humidities.
Yes, that's correct. The first slide was just an example of how we represent it, and the slides at the end where the results are the actual ones. Yeah, sorry about that confusion.
Nelson Britta of Modular, question or comment. The overall external boundary insulated area of this study corresponds to only about 20%, allowing humidity to find alternate paths of flow. Can you debate about the impact of insulating 80% of the boundaries and leaving only 20% uninsulated area to deal with water vapor flows?
Yeah, I mean, that's something that obviously we've addressed in terms of the way that respecting the cornice. We know that there's ventilation flows from maybe the adjacent walls. There could be different location of air coming into that cavity. I mean, when we're focusing on a wider scope, it can be. You've got to analyse all those points. In this case, it was just this moment in time and that location. So yeah, that would be a further kind of analysis.
Mm-hmm. A question from Martin Jarvie of KLM Partnership. Do you know whether Historic Scotland would be happy to install an internal wall lining to an important historic building as carried out in your case study? Also, do you have any capital cost versus energy cost saving to establish the payback period, which is always a major factor when it comes to carrying out such measures?
Well, two questions there. The first one, the Historic Scotland one, it's not really up to me, but I'm sure Historic Scotland are interested in doing trials in a lot of building types and situations. It would really be locating a building of that type. The second one, sorry, what was it? I can't read it.
Okay. About the capital cost versus energy cost savings.
Yeah, I mean that would be, I think, a next stage in terms of we were purely looking at the technical aspect of how this wall was performing. I think an overall kind of heat loss aspect and how that impacted on the overall energy bills, and would be a good stage to take forward.
I think all I would add to that would be that if we make the assumption that external wall insulation isn't possible because of the stone finish of the stone facade, or other issues, flatted dwellings and tenements, insufficient pull-out tests on the substructure, etc., or even flood zones for that matter, being able to come up with a system that can be installed quickly without the cost of having to strip the existing finishes off and reframe and install costly natural materials is what can make this all work. Maybe that will change when the economies of scale kick in for the natural materials, and I certainly wouldn't have a problem with that if that was the case. But it's safe to say that it would provide an option that would certainly be at much less costs than the alternatives of stripping the walls back.
A question from Philip Butler of Mud and Wood. The existing cavity behind the newly applied insulation seems to be a critical element to reducing the risk of condensation. Have or will tests be carried out with the insulation applied directly to the wall, or situations where the wall was completely covered? Should cavities always be included, in your opinion?
I think this should be. I mean, we've proven not just in this example and in others that that kind of slightly ventilated aspect inside the cavity is proving to kind of emphasise this migration of humidity upwards. So in that case, yes. But I also think that air can also be a big influence on the thermal performance on walls in terms of the U value. So it's kind of like two sides of the coin in a way. By adding a cavity, you're obviously not following this full path of thermal kind of covering of the wall. So in terms of the thermal aspects, I would say fully filled cavities are good, but for humidity aspects, it's a good thing. So maybe a kind of boundary between both would be ideal.
Interestingly, all the systems that I can think of for IWI on solid walls with a hard plaster finish currently include the requirement to strap out the walls to create a cavity, and I think there's also the threat of the solid wall sweating or moisture penetration after heavy wind-driven rain. I suspect might be another reason why some of the systems either use a material that is closed cell, or if they use timber straps, it may be fixed through a DPC.
Okay. A question from Alan Cullen of Lato Maintenance. Did you assume the small cavity was slightly ventilated, or did you carry out air velocity tests?
No, we just monitored it well and calculated as slightly ventilated. We are trying to work with Historic Scotland on monitoring inside the cavities, or maybe using tracer gas to see where air is kind of originates and where it kind of dissipates to. With that kind of further analysis definitely down the line.
Question from Ben Balfour, Ben Balfour Architect. Your test seems very limited in scope. Do you think you have done enough research to be able to positively recommend this strategy?
Well, I mean, I recognise that we've only done tests on a monthly period and it's the very beginning of the heating season. That's why BCA have instructed us to continue a whole heating season. Now, ideally, it would be recommended to do a full yearly study with our probes in, just to get both a winter and a kind of summer period. But in this case, we tried to concentrate on the winter element. So I think in terms of the scope in this presentation, it's just 1 month, but I think the results we obtain after 6 months would be quite interesting and compared.
Question from Dave Tremlin of Conservation General Services. I accept the desirability of a cavity, but does this rule out dot and dab installation of insulating boards?
It depends on the origin of the ventilation. In terms of dot and dab, it's static, it's stagnant.
I think
what were your views?
If you had a hard plastered solid wall, I believe that certain manufacturers would be happy to dot dab their product straight onto the hard plastered wall in certain exposure zones, and I think there is a qualification on what exposure zone you're allowed to do it. Yeah, so if it's dry lined, I don't know that it's an issue.
Okay. Question from Graham Drummond of Passive House Associates. I seem to remember a previous webinar featuring the in-situ fulfill of the cavity behind lath and plaster with poor foam for a house in Aberdeenshire, I think. Can you please comment on this different approach? This was a webinar on the study undertaken by Robert Gordon University. If you if you have watched it,
I haven't watched it, but I know of it. That's something that Historic Scotland have been doing quite a lot as well, filling in those cavities. And I mean that's ongoing monitoring. Again, that we've been monitoring that for a full year. So those results should be coming in the kind of end of spring. But yeah, that's why Historic Scotland are quite interested in doing a lot of these trials, and BCA have been part of that as well in the installation of it. And there's other materials. I mean, you've got cellulose, you've got beads. They're all kind of good to monitor and to see how how that wall performs. So.
Yeah, I haven't seen that particular webinar either, but I think it was maybe Eisenine that was used, which is an open-celled foam or a self-draining foam, so any moisture would be allowed to drain through it. It wouldn't have as good a vapour resistivity as PUR. PUR is something we can install, but I suspect if we tried to install it in a plaster and lath wall, we would just blow it right off the wall because it's quite ferocious in its expansion.
A question from Eric Parks. Are there any plans to do further research on a more extensive application of the solutions proposed here, i.e. to understand what happens at intermediate floors, for example?
Yeah, again, with Historic Scotland, we're trying to do some further studies, and both my colleagues at the Scottish Cemetery Centre we're looking into, again, tracer gas and maybe looking at monitoring the origin of different flows of air and how that, and intermediate floors might be one of those areas. Also, roofs, very important to monitor. The location of and the origin of air, whether it's ventilated or not, and see how that influences.
I think other reasons to do further research and other areas of further research we've done at the moment is also to look at the cold bridging effect of other planes, whether it be internal walls or internal floors, and so far the results that we've got it's been good again, because the other benefit of the cavity and the thickness of the plaster and lath is that the cold transfer doesn't seem to be as bad because because the surface is isolated from the mass of the stone wall, and any cold points at internal wall junctions would be occurring behind the line of the insulation. So yeah, it's definitely something that needs to be researched further. But so far, what we've seen in the modelling and other research has been good news as well.
Okay, thank you very much. Here is one comment from our viewer Dave Tremlin of Conservation Joinery Services. Excellent presentation. Thanks, guys. Thank you very much, Dave. And we are now close to the end of our webinar. There seems no more questions are coming. So I would like to thank you both for the presentation and comments, and to our online viewers also for the questions they have asked. And just to advise about forthcoming webinars, on 21st of February, that is tomorrow, we have a webinar on solid timber systems, nail and doweled plank. The speakers are Deb Turnbull of Center for Offsite Construction and Innovative Structures at Edinburgh Napier University, and Neil Sutherland, architect at Makar in Inverness. Then on